Start. So today we will have the tutorial questions for the stress transformation or the principal stresses. Okay, and this is our first example. We have element, small element, and we have stresses, vertical stresses or stresses in the vertical direction, 200 megapascal, and we have shear stresses, 350 megapascal. Okay, and the requirement is to find the principal stresses for the following point or the following element. Okay, so now start using Paint. For the principal stresses, or stress transformation, if we have a discrete element or a small element in a beam or a member, okay, if we extract this beam, this element, so this element may be subjected to two types of stresses: normal stresses in this direction. As you know, this is horizontal direction, so this sigma x, and also maybe under vertical stress or stresses in the vertical direction, sigma y. Okay, sigma x and sigma y, we call them as normal stresses. Okay, we may have another type of stresses, which is shear stress in this direction, tau xy, and also in this direction, tau xy. So this is stress, tau xy, we know as shear stress. Okay, so this is the general description or the general alignment of stresses we may have. So we may have sigma x, sigma y, and tau xy. Sigma x, stress in x direction, or we can call it normal stress. Sigma y is the normal stress in y direction, and tau xy is the shear stress. So this is a general case. We may have just three types of stress. Okay. These stresses, we can transform them in two directions or in two axes, which is principal stresses, or this stresses in principal axes. We can call this principal stresses is maximum and minimum stresses for this element. Okay, so we can call this as a resultant or the total stress on this element. Okay, these two stresses, sigma maximum, or we can call it sigma 1, and sigma minimum, or we can call it sigma 2. The formula for these two stresses is sigma x plus sigma y divided by 2 plus or minus the square root for sigma x minus sigma y divided by 2 all to the power 2 plus tau xy to the power 2. So this is the general formula for the principal stress, where plus for sigma 1 and minus for sigma 2. Okay, so if we ask it for the principal stresses for a discrete element, we need to know sigma x, sigma y, and tau xy. Okay, so now again, sigma max minimum equal to sigma x plus sigma y divided by 2 plus or minus square root sigma x minus sigma y divided by 2 to the power 2 tau xy to the power 2. Okay, we should know that the sign convention for sigma x and sigma y. The sign convention, as you know, sigma x is positive if we have tension, stress. Sigma x is negative if we have compression, stress. If we want to show this, so we have two cases. If this sigma x in horizontal direction, so what you think, this is tension or compression? Here the element is under tension, so sigma x is positive because it is tension. The other case, if the stress is pushing in x direction, so sigma x will be negative value because it is compression. Okay. For sigma y is similar to sigma x but in y direction. Sigma y may be positive or negative. Sigma y will be positive in tension and negative in compression. So if this is the element and this is the direction of sigma y, so this sigma y is pulling the element, so sigma y is positive. The other case, if we have this element and we have sigma y pushing the element, so sigma y is negative. Okay. Okay, thank you, Nick. For tau xy, if you have a look on the equation, so sigma tau xy is always under cubic, so it doesn't matter the sign for it, but if we want to know the sign, if this is the direction of tau, so this is negative tau, and the other case, if this is the sign of the direction of tau, so this tau is positive sign. Okay, so now we know the equation, the general formula for the principal stresses and how we can apply in the equation. Okay, if we return back to the equation we have, so this is a simple element, as you can see. Okay, under two stresses, this is sigma y and this is tau xy. So in this case, sigma x is not available, so sigma x equal to 0. Okay, I will give you 10 minutes to solve this example, and then we can I can solve it for you again. Now we'll solve this one with you. So for question 1, we have small discrete element, straightforward application for the formula. and we have only stress in y direction, 200 megapascal, and we have shear stress in this direction, 350 megapascal. The requirement is to find the principal stresses sigma 1 and 2 for this element. Okay, so our general formula for principal stresses, sigma 1 2 equal to sigma x plus sigma y divided by 2 plus or minus sigma x minus sigma y divided by 2 to the power 2 plus tau xy to the power 2. So we need to know sigma x, sigma y, and tau xy. From the question, we know that this is sigma y because it is in y direction. So sigma y is equal to 200 megapascal. With tension or compression, as that stress is pushing the element, so this is compression. So sigma y will be negative. For tau xy, tau xy will be 350 MPa, and uh, as we said in the sign convention, this is negative shear, and you can neglect this sign because it doesn't matter as it is under the cubic. So now we know sigma x, sigma y, and tau xy. For sigma x, so for sigma x in this problem, sigma x is not available, so sigma x is 0. So if we substitute it in this formula, so sigma 1, 2 will be 0 minus 200 divided by 2 plus or minus sigma x 0 minus minus is plus 200 divided by 2 to the power 2 plus negative 350 to the power 2. That give us sigma 1 2 equal to negative 100 plus or minus 364. So sigma 1 will be negative 100 plus 360. Sigma 2 would be negative 100 minus 364. This give us plus 264 MPa. Positive means tension, and this give us minus 464 MPa, which is compression. Okay, and as we said, we can call sigma 1 as sigma max principal, and sigma 2 is sigma minimum principal. Okay, so this is the result of this question 1. Do you have any problem with question 1? I think it's just straightforward. So now we can shift to the second one, or the second problem. This one is combining two ideas. First, we need to find the stresses because as you see the element or the cross section here, and here is the element we need to study, element A at A, this is our element. So stresses sigma x and sigma y and tau xy is not defined, so we need to find them first. Then the second step is to find sigma 1 and sigma 2 at point A. This is A. Okay, so it has two steps. And the requirement again here, we need to find the principal stresses for point A. Okay, so now shift to the paint. to explain this one. So for question 2, we have simple beam. And we have 12 kilonewton applied here. And the distance here, this is 4 meter. This is 1 meter and this 2 meter. And given that we need to find the stresses at element A, this element A is 75 millimeter from the base or the bottom surface of the beam. And if we make a cut in this section and this beam, the cross section of this beam AA is a solid rectangular section, 300 millimeter height and 200 millimeter width, and this is the cross section. And the requirement is to find the principal stresses at element A or at A. As you know, if we extract this element here, so we need to know sigma y and sigma x and tau xy. So we can find sigma 1 and sigma 2. Okay, how can we find tau xy and sigma x and sigma y? So we need to find sigma x, sigma y, tau xy. Sigma x and sigma y, as we said, are normal stresses, and tau xy is shear stresses. So this problem is combined three topics or three ideas. We need to find the normal stress and shear stress, and then second step we need to find the principal stress. Okay. So first of all, we need to find sigma 1, sigma x, and sigma y. If we convert this beam, so this beam will be something like this. This one is roller and this one is hinge, and we have a load somewhere here, 12 kilonewton, at a distance 3 meter from this support and 4 meter from this support. So first of all, we need to draw the bending moment diagram and shear force diagram. Shear force diagram will give us a step to find tau xy. Bending moment diagram will lead us to find sigma x. Okay, and for your information, in this problem, sigma x, sigma y will be 0. Why sigma y is 0? Sigma y is 0 in beams. Okay, this you need to keep this in mind. In beams, no sigma y, because if this our beam or this our beam cross section, we have applied moment in this direction or in this direction, mx or mx. So this mx only give us sigma x. So sigma x will have value, but sigma y will always be 0 in beams. Okay, so we're only searching for sigma x and tau xy. Now we'll shift to the second slide for this one. We have simple beam again, very straightforward beam. 12 kilonewton here, and the distance is 3 meter and 4 meter. If this A and this B, so how can we find, or how can we draw shear force diagram and bending moment diagram? We need first to find the reactions. How many reactions we have? We have YA and YB and XB. If we apply if X equal to 0, so XB should be 0. Summation Fx. So the second step is to apply the moment equation at A equal to 0. What cause moment at A? What cause moment at A is 12 kilonewton and YB. So we have YB multiplied by 7 in this direction. We said before anti-clockwise is positive, so it is positive. Minus 12 because it is rotating in this direction. So minus 12 multiplied by 3 equal to 0. This gives us YB equal to 5.143 kilonewton upward. If we apply summation Fy equal to 0, so we have Ya plus Yb minus 12 equal to 0, and we just find that Yb is 5.14, so Ya will be 6.857 kilonewton and upward as well. Okay, so now we find the reaction. Second step is to draw the shear moment diagram and bending moment diagram. As we know, we have to draw datums and guidelines. This is our datum for shear, and this is our datum for moment. Okay, and how many section we need, or how many cut we need? Is cut 1, cut 2, cut 3, cut 4, end and the beginning of the beam, before and after the concentrated load. So what cause shear at, this is 6.857 and this is 5143. What cause shear at 1, at cut 1? The reaction. So here we have to go upward 6.857 kilonewton. From 1 to 2 we don't have any forces, so straightforward, or straight line, sorry, kilonewton. From 2 to 3 we have 12 kilonewton, so this will cause us to go downward up to 51.143. Then from 3 to 4 we don't have any forces, so straight line up to 15143. Then after the cut we have the reaction, so we again go to 0. So here we start from 0 and then end with 0. This above the datum positive, below the datum is negative. For the moment, how can we draw the moment here? The moment at the beginning of the beam is 0. The moment at 2. What causes moment at 2? What causes moment at 2 is the reaction. So M at 2 will be the reaction 6.857 multiplied by 3. Okay, this gives us the moment will be 20.57 kilonewton meter. So the moment here would be under the datum 20.457, and we don't have any uniform load, so we connect with a straight line. The moment at the end of the beam is 0, and we connect with a straight line. So this positive moment. Okay. So this is the shear force diagram and bending moment diagram for the whole beam. But if we return back to the problem, here, we need to find, or we need to study at this section at A only. So we need to find the moment and shear at A. So if we return back to the bend, we need to find if this A here, A is only 2 meters from the support here. So we need to find the shear at A, this shear force at A, and also the bending moment at A. So M at A, or at section A, or at element A. Sorry, we'll start with shear. Okay, shear force at element A will be 6.857 kilonewton. Okay, bending moment at A. The bending moment at A will be 13.714 kilonewton meter. How can we get this? Again, this is our drawing for shear. This positive, this negative, shear force diagram. This was 6.857 kilonewton, and this 5.143. So if this A here, 2 meters from here, so shear at A is 6.857. For the moment, this is our moment drawing. This was 20.57 kilonewton meter, and we need only to find the moment at A here. How can we find the moment here at this point? Okay, how can we find this? This is 2 meter and this is 3 meter. So M at A will be 20.57 multiplied by 2 divided by 3, because this is a percentage triangle here. So we know this element. So we know that
can't we just say 6.875 times 2 will be?
This is another way. We know here the reaction as well, 6.857 kilonewton, and this is 2 meter. So the moment here will be 6.857 multiplied by 2. Both of them give us the moment 13.714. You can find the moment, but by any way you want. Okay, it's up to you.
The one you did first was unitary method, isn't it?
Yeah, this one.
Yeah.
Kilonewton meter. Or what you said again? Sorry. You said
Like
the units?
unitary method, I'm just saying the first one, the 20.571. So you first calculated it per meter and then multiplied it by 2.
Yeah, no, this is just the moment. You mean this value? This value is the moment under the load, the maximum moment for the beam. But he asked you only to find the moment at A.
Yeah.
So we need to find the moment at element A here. So we need to find the moment at A, which is 2 meters from the support.
Yep. I was just saying the first method that you did, for finding the moment, that 20.57 times 2 by 3.
Yeah,
So
yeah, yeah.
it
This
may
is
it
yeah,
finding the moment per meter and then multiplying it by 2.
yeah, yeah.
Yeah.
Okay, so now we know that the shear force at element A is 6.857, and the moment at A, mx at A is 13.714 meter. The shear will give us tau xy because shear force causing shear stress. The moment mx will cause normal stress sigma x. Okay, if you return back to your memory, we have tau xy formula equal to, or tau shear stress, tau. The formula for tau, V multiplied by Q divided by I multiplied by T. And the general formula for normal stress, sigma x equal to normal stress equal to mx divided by ix multiplied by y. So now we are applying two formulas we know before, tau and sigma. Okay, to apply these two formula, we need to know ix, and also we need to know q. Okay, so now before proceeding in the problem, so we need to find ix and also q. If we return back to the section was a solid section, 200 millimeter by 300 millimeter. This is symmetric section, so x axis and y axis in the middle of the section, and this will be the centroid. Okay, ix will be the parallel to x 200 multiplied to the perpendicular to x 300 cubic divided by 12. This gives us I equal to 4.5 multiplied by 10 to the power 8 millimeter to the power 4. This is Ix. For Q, if we return back to the beam, it was given that the element A is somewhere here, this is A, at a distance of 75 millimeter. So we are calculating the stresses here. This is at A is here at 75 millimeter. Okay, so we need to calculate Q at this line. So this will be the area we are calculating Q for, because A is here. So we need to calculate QA, which is 75 millimeter from bottom. Okay, Q is equal to A multiplied by Y, area multiplied by distance. What area? This is the area, the sky blue area. What is the distance? The distance from the centroid of this area?
150 mile.
Yeah, to the CG. So this is Y. So Y in red is our Y. So QA will be, how can we know the area? Area is 75 multiplied by 200, right? And what is Y? Y, if this 75, so half of this is 37.5. So the distance we need to know is this one. How can we find this one? If the whole distance is, the whole height is 300, so half is 150. So
150
our y,
minus
yeah, 150 minus 37.5, which is 112.5.
Yeah.
So this gives us that Q at A will be 1.6875 multiplied by 10 to the power 6 millimeter to the power 3. This Q. So now we know our missing parameters I and Q. So now we can proceed in the solution. So for tau xy will be again V multiplied by Q at A divided by Ix multiplied by T. So tau xy, V is the shear at A, right? What is the shear at A? We just
6
calculated.
point something.
Yeah, 6.857 kilonewton, right? Multiplied by Q, just calculate 16875 multiplied by 10 to the power 6. Divided by I, 4.5 10 to the power 8. Multiplied by T. What is T here?
The distance of the area from the center.
No. If you return back to the shear equation, T was the width of the section
Oh,
at point of stress, right? If we are calculating the stress at A. So what is the width of the section at A?
150 minus 75. Oh, width. Oh,
Yeah, width, not
200.
height. 200. The width of the whole section is 200. So this still 200 millimeter, right? We just need to be careful with the units. Here, this is millimeter, right? Cubic. This millimeter. This millimeter to the power 4. And we said before we need all the unit to be Newton millimeter. So the shear force was in kilonewton. How can we
Times
convert to?
1000.
Yeah, so we need to multiply this by 10 to the power 3 to convert it to Newton, right? So after finalizing this calculation, there will be 1.1286
856.
MPa or Newton per millimeter square. So the stress or the tau 0.1286. Okay, do you have any problem with tau?
No.
Okay, the only idea is that Q is at the section he mentioned or the point he mentioned. Okay, now we can shift to the sigma or the normal stress. How can we find sigma x at A? Again, sigma x at A is mx multiplied by y divided by I. Okay, and here is the section we have, and this is x-axis, this is y-axis, and this is the centroid. Okay.
Yep.
And m, this is m. X, we just found mx is 13.147 kilonewton meter. Or sorry, 714. Okay. So now we know sigma x will be m 13.714, and I will multiply by 10 to the power 6 to convert from kilonewton meter to Newton millimeter. We need to multiply it by 10 to the power 6. Divided by I is 4.5, 10 to the power 8. Okay. What is y? Again, A is here. This is point A. Point A is at a distance of 75 millimeters from the centroid. And here we said before y
from the bottom
is the distance from
Isn't
point.
a 75 from the bottom?
Yeah, 75 from the bottom, and because this is 150, so 75
Oh,
from the bottom and 75 from the centroid.
okay.
Okay, and again we said that y is a distance from point of stress to centroid, right? Point of stress is A and centroid is here. So this is Y. Y, how much for Y in this case? Y will be
75.
75. So finally, sigma X is
2.6.
2.2857 MBA. Okay. And now we get sigma X and tau X. The final step or the final stage in our problem is the principal stresses. To know the principal stresses, this is our element at A, and we have sigma X and tau X, Y, right? Here, sigma X is positive or negative 2.2857 MBA. This is, you need to keep in mind this idea. Here, if we return back to the moment here, the moment is causing again tension in one side of the beam and compression in the other side, right? For A in the tension side or compression side? Can you know this one? Point A is in tension side, so sigma X at A is positive 2.2. Okay, so when we finding the stresses, sigma X is tension, positive 2.2, not negative. Okay, if we have a point B here, this is B. Point B, in another problem or another situation, point B is in the compression side, right? So sigma X will be negative 2.2. Okay, so this sign because A in tension side. Tau xy doesn't matter the sign, but tau xy in this case is 0.1286 MBA. So 0.1286 MBA. And now we can find or substituting in the formula sigma x plus sigma y divided by 2 multiply plus or minus root the square root for sigma x minus sigma y divided by 2 square plus tau xy square. Here tau sigma y is 0, so sigma 1 2 will be positive 2.2856 plus 0 divided by 2 plus or minus 2.2856 minus 0 divided by 2 square plus tau xy 0.1286 square. This gives us that sigma 1 2 will be positive 1.428 plus or minus 1.15. So the final result sigma 1 will be positive 1.42 1 plus 1.15. This gives us positive 2.29 MBA, and sigma 2 will be plus 1.428 minus 1.15. This gives us minus 0.0072 MPa. The positive sign means tension stress or tensile stress. The negative sign means compressive strength. Okay.
Yep.
Do you have any problem with this
Yep, but
question?
if you could go back to the slide where you found the moment for finding this principal stress, I just got a question from there.
Okay. The calculation of the moment.
Yep, where you found the moment at point A.
Okay.
Yep.
Okay, you can see now.
Yep.
Okay.
So yep. My question is why it's positive here? Because it's clockwise for point A. It's clockwise, so it should be negative instead.
You mean the moment or?
Yeah, moment. Yep.
Yeah.
We are using it as plus 13714, but it's in clockwise direction as we can see.
No, if I will explain to you now. So I will go to bint. Here, as if you remember, when we are drawing a moment,
Yep.
we have B, so the direction B is divided by 2.
Yep.
So if we want to draw a moment, a bending moment diagram for this one. So what we are doing, this bending moment diagram, we have cuts 1, 2,
Yep.
3, 4. So this is our guidelines. The moment in the beginning of the beam is 0 because no forces. If we study this part, so no forces, so the moment is 0. But the moment at 2, what causes moment at 2? M2.
P by 2.
B divided by 2 multiplied by the distance.
Distance. Yep.
If this L by 2,
Yep.
so L by 2, this gives us the moment value is BL divided by 4, right?
Yep. Yep.
And we said before that the sign above the datum is negative and below the datum is positive for moment,
Yep. Yep.
if you remember.
Yep.
Okay, and we said that we are putting the value of the moment with the tail of the moment because the moment is rotating in this direction, the force
Yep.
is rotating in this direction,
Yes.
so the tail is under datum, right? So this moment will be under datum. Okay, so the value of this moment will be, I put it here. Why I put it here? Because the force causing this moment is causing moment with tail under datum.
Okay.
Okay, so this value of moment will be BL divided by 4, and we can connect this two by straight line, and also the moment here will be 0, so you can connect with a straight line. This moment with positive sign or negative sign
First step.
because it is under
The
datum,
data.
and
Yep.
we did say under datum is positive. Okay,
Yep.
so if we again reversing this to the section, if this our cross section x
Yep.
y, this moment at A or at this section, let's say section 1,
Yep.
the moment is rotating in this direction. Why I put it in this direction, not in the other direction?
It was similar to the one in the first diagram because the tail is under the datum.
Yeah, because this moment is causing tension is in the bottom side or under the datum, so the moment should be causing tension for this half and causing compression in the other half. Okay, because this diagram, the yellow diagram, means the tension side. So this means the tension side will be the bottom side, not the top side. Okay?
Yep.
Okay, so this means that this is our moment and it should cause tension at the bottom side and compression at the top side. Okay, did you get it?
Yep. Um, so, can you also go to the diagram where you draw the cross section and the moment for the caution that we just did?
Okay. Do you mean this one or the diagram?
I couldn't see, sorry.
Okay, sorry. You see now?
Yep. So the moment one. Yep.
This one?
Yep. So in the diagram that you just showed me, arrow was in the opposite direction, but here the arrow is from. It's from the it is for starting from the below the datum, but it's on a different side. It's on right hand side here.
It doesn't matter because you are. I
But
know what you mean.
but it will cause the same thing. It will cause tension at the bottom.
Yeah, yeah, yeah. This is
But
similar
no,
to this one.
got
This
it.
one is similar to this one.
Yep.
Okay,
Yeah,
because
got it.
we are in 3D. If we are
Yeah.
in 3D, so what we mean is the moment, whatever the moment is.
Yep.
Oops, sorry, what happened? Okay, I'm back here. So what we mean is I need to undo this one. Okay, so if this our x-axis,
Yep.
so the moment is rotating in this direction. So it causes positive sign or tension in this side
Yep.
and causing compression in the other side. Doesn't matter if you have a look or have a projection of this drawing. So
Yep.
it may be the red one or the sky blue one. Doesn't
Got it.
matter. Just what we concern about is this half is under tension
Yep.
and the other side under compression. Okay,
Got it. Thank you.
no worries.